All right. So we have already progressed quite far in our study of linear control, of basic ideas of control theory. Specifically, we recently learned this new sort of chunk of control theory related to observers, state estimation, and we connected it to more general class of controllers, dynamic controllers, as I described them, with memory, with internal state, right? PID controller was a good example. Low pass filter was a good example. Lüneburg observer is an example, right? So there is this class of systems, quite interesting. Now, let us go back a little bit to sort of the basic questions that we can raise in designing such controllers, like controllers in general. For instance, we can raise quite a fundamental question. Given a system, is it possible to find a controller that would stabilize it? Is it possible to find a controller that would drive us to the desired state, from the current state to the desired state? Is it possible? Sounds like a legitimate question, quite simple. Similarly, we can ask a question. Given a system, given its output matrix, like its measurement matrix, is it possible to design an observer? Is it possible to design an observer which would be able to observe, so estimate the state? Or is it not possible? And somehow we skipped those questions. Instead, we directly started to talk about how to design such a controller, how to design such an observer, right? We know how to design them. For example, using the theory of Riccati equation, posing a problem of linear quadratic regulator. That is how we design controllers. And it happens to be also observers. We design them the same way. Or using pole placement. That is another way we can design controllers. We know even for what we design them, for stability, right? But there is no moment where we can say, well, how do we tell that this is even possible, right? And this question is, as you can imagine, very practical. Is it possible to design a controller? Is it possible to design an observer? Why is it practical? Because imagine your algorithm fails. Imagine you try to design a controller and your algorithm does not produce a result. If it is, for instance, pole placement, may very easily fail. You ask for poles which are impossible for the system. The system cannot achieve poles that you are asking for. All right, let's say it is LQR. You try to solve it, and your numeric solver, the solver that tries to solve your quadratic Riccati equation, tells you there is no solution. Or, fail to find a solution. At this point, you have to ask yourself, am I asking something bad? Am I asking something that is difficult to achieve? Is my algorithm weak? Like maybe my algorithm is not designed very well? Or is the system fundamentally uncontrollable? After all, you can easily imagine a system which describes two motors. One is connected to the source of power, another one is not connected to anything. Those motors cannot, like, the second motor cannot be controlled by the source of power of the first. You can describe them as a system of equations. Very easily, you can describe a system of equations of two motors at the same time, one with input and one without input. The output of the second motor cannot be controlled, no matter what you do. And it is not a question of doing pole placement or doing LQR or anything else. It is a system, simply physical fact that the second motor is not going to rotate anywhere, regardless of the current you are putting through the first motor, right? So somehow it is an interesting question. That is the topic of the lecture. How do we answer this question systematically? How do we make a answer which can guarantee, yes, does exist a controller, or no, there doesn't exist a controller that can do it? All right, let's begin. So first, just definitions of what those what those words imply. So first of all, there is a term controllability. Right? Controllability. The way I define it here is system is controllable if on the interval from 0 to time final, it is possible to find such control input u of t that would drive the system to a desired state from any initial state. So there's any desired state, any initial state, we don't know those. But we want to ask if it is always possible to find such control input that would, given those two numbers, desired and initial, can drive us from the second to the first. Right? That is controllability. If it is always possible to find such control input u of t, then it is controllable. If it is not always possible to do it, then it is not controllable. We can do the same with observability. So I will just quickly define it here, but we would study it a little bit later. So system is observable on an interval if using output of the system on this interval, it is possible to estimate exactly the state of the system x at the last point of the interval, given any initial estimation error. Right? Or alternatively, system is observable if on the same time interval, if any initial state can be determined just by studying the output of the system. So basically, the difference between those two definitions is this. In both cases, you have a system. In both cases, you have output, and you have interval. One definition tells you should be able to find out what x is at this moment. Another definition tells you should find out what x is at this moment. Right? That's the difference. All right. So observability, we'll come back to it in a bit, but first we will discuss controllability. So to remind you, the idea is we should be able to get our x from any initial state to any desired state in finite time. Now, it should also be possible here to extend this t final as far as we want. So it's it doesn't have to be a small number. We can extend it as far as we want. So the smallness of this time interval is just how I should put it. Like we can think of it whether or not we want this to be approaching infinity, TFF or whatever. In any practical system, as you can imagine, there is no question of approaching infinity, right? Like no technical system actually approaches infinity. There is no technical process that goes on for like 10,000 years. So the idea of stability that somehow requires infinity is a little bit strange, right? On the other hand, for a lot of definitions, a lot of sort of like derivations, we sort of assume that TF is, can be as large as we want, approaching infinity and so on. So this whole thing with time bound is a little bit, a little bit loosely defined, I'd say. Yeah. All right, good. Now, let's go on. Now, okay. Next, what we want to do, you can see this definition. Now, next, what we want to do is to see if we can make sense of this requirement for discrete systems. For discrete systems, it is very easy. That's why we are going to do it for discrete systems. For continuous time, we can do it as well. I would show you after we are done with discrete systems. So first we do simple derivation, then we do complicated one, right? Both are useful, so no problem at all. All right. Now let's consider discrete LTI defined like this. So next x is equal to the previous x times a, previous u times b. The first step is to study how x changes with time. So consider x number 2, second element in this discrete series. It is equal to a times x number 1, b u number 1. All right, fair enough. Next, consider x number 3, so the third element in this series. How do we compute this one? Well, it is a times x number 2 plus b u number 2. Now, this guy, we can take x number 2 from here and substitute. And we substitute here. What we get is, instead of x2, we get a x1 b u1, right? Next step, we open the brackets. Like, I mean, we can open the brackets. We're not going to do it here. But if we want to open the brackets, we'll have a squared times x1, a times b u1 plus b u2. Right. For now, I'll just keep the brackets closed. One more step, x number 4. This ax number 3 plus bu number 3. All right. Instead of x number 3, we take what we just discovered on the previous step. We put it here. You can see I just copied it, right? A times x3, which happens to be a times x, a times b times u, b times u2. Okay. Plus this b u3. All right. Okay. And so on and so forth. So what will happen if we continue is we would have those brackets which would keep growing. There'll be a times a times a for the third step, a times a times a times a times a for the first step, and so on. So the number of a's here would be equal to this index minus 1. Then there will be internal bracket with b times u1, and then number of a's multiplying this b would be this index minus 2. For this b, the number of a multiplying it will be this index minus 3, and so on and so forth. So the final formula is this, where we have x n at the step n plus 1 is equal to a times to the power n x1. So let me show you where it comes from. So this comes from here, right? Then a to the power n minus 1 times b times u1, that comes from here. Next one would come from here, and so on and so forth. So the last member of this series is b u sub n. So u with the index 1 less than index here. Just like here, you can see, right? That's it. So this series looks like this when we do n steps forward. Good. So we have this expression. Now let's analyze this expression. I reproduce the expression here on top of the slide, right? Now, what can we do with it? Well, what we can do with it is we can take this guy and this guy to the left-hand side. I can write them like this. Okay. The rest, so all of this, we can leave on the left-hand side, but we can separate u into separate vector. So concretely, we take this guy, we see that it is multiplied by u1, right? We write like next guy somewhere here. It is multiplied by, in this case, u n minus 2, is going to be some other. And like the last guy, b, is multiplied just by un, right? So the idea is we have all those things on the right-hand side, each multiplied by u sub n, u sub n minus 1, u sub n minus 2, etc., etc. Right? I think it's quite clear. It's a little bit difficult to like explain because the words are clunky, right? But I think the mathematics here is quite clear, right? We just take how do I put it? Like this u is this u multiplying this expression. Next one would be multiplying something else, etc. And the last one, this b, this u, like this b times this u, you get this bu, right? But quite clear. All right, good. Now let us consider what it means. What it means is this. We have on the left-hand side expression that contains our two desired things. One is initial conditions x1. Next is x final, xn plus 1. Remember, in the definition of controllability, we were thinking about some kind of x final that we should reach from some kind of x initial, right? Let's consider those two as x final as x initial. Basically, what it means is we have some expression here, and regardless of what value source vectors take, the expression on the right-hand side should be able to satisfy this equality. All right, okay. But what values can this expression take? And here is a very nice and simple trick of thinking about it. Well, x1 can take the value 0, right? It is a legitimate value of x that initial conditions can be 0. Right? We cannot ignore the value 0. 0 is a legitimate value. In this case, this goes away, right? And what is left is only this guy. And this guy, as we said, can take any value. So it doesn't have to be something particular. It can be anything. With that, this expression overall takes all possible values, right? So notice that if we now relax this condition, we relax the fact that x1 has to be 0. We say x1, let it be not 0, let it be something else. We cannot possibly find more vectors that the left-hand side can take. We already said that any vector can happen on the left-hand side. So basically, this trick just quickly proved to us that this contains all possible vectors. All right, good. That's the idea. All possible vectors. Now the question becomes, can we produce all possible vectors by multiplying this matrix by this vector? That is the question. The question is purely algebraic. It has a purely algebraic answer. So if you take a matrix and you want to ask, can it produce every possible vector as output? Basically, what you are asking is whether or not it has n in the n-dimensional space, right? If it has n independent rows, right? N independent rows. In other words, which is exactly the same, you're asking if the rank of the matrix is at least n. That is the same thing said in different words. Or if you're more familiar with terminology regarding fundamental subspaces, you can say is the column space of this matrix n-dimensional? Regardless what you like range, column space, image, they should be like n-dimensional. All right, 3 ways to talk about it. For us, it is sufficient. I think rank would probably be something that you studied in your linear algebra course. So it is sufficient to say that this matrix has n-dimensional, has n independent column rows. So the row rank of the matrix is n, right? So that is the answer. That is the criteria. That's the criteria. If we want any possible vector to be available here, the matrix here has to have n independent rows. Okay, all right. Now, the criteria for controllability is written like this. For a discrete system of this type, it is controllable if its controllability matrix, written like this, is full row rank. So rank of C is equal to n. Yeah, so it cannot, yeah, I think if you are familiar with thinking about rank in terms of just computing number or like rank as a, like passing the matrix through some kind of calculator that calculates rank is good enough. Is good enough, right? Um, we insist we talk about row rank, but mostly what the reason we talk about rows is specifically because we have n rows and we want to understand them that all n of them are independent. That is kind of like the idea why we stress this like full row rank. You're not going to see independent columns for this matrix unless B is a single vector, right? Just by the size of this matrix, it is n rows, but the number of columns is n times the number of columns in B in control matrix. So in general case, you're not going to see independent columns for this matrix. So we say full row rank to indicate that what we care about is the fact that rows are independent from each other. We don't care if the columns are all independent. In fact, they cannot be all independent from each other if there is a more than one vector in B, right? There will be just, it is a wide matrix, right? The shape of the matrix is like this. Cannot have independent columns in general. Only if B has a single vector, then have independent columns. Yeah. All right. Good. So this is a criterion. This is a criterion, and you can see how we arrived to it, right? Very simple. We just computed what x1, x2, x3, x4, etc. is, wrote it as a system, and noticed that the right-hand side should be everything, should be able to produce everything by definition of what controllability is. Therefore, this matrix has to be a full row rank. That is all. Like the argument is very simple. Now, what you can argue about is that it is very strange how I conveniently stopped at this x n plus 1, right? Just conveniently stopped there. Like instead of going forward, instead of saying, okay, let's take n plus 2, n plus 3, and so on, I just stopped right here. And I think your intuition will tell you, well, just go on forward. Maybe you will eventually achieve this output, right? You cannot do it in n steps. Try more steps. You would achieve it in more steps, right? This intuition is correct in terms of real engineering world. Because in the real engineering world, your steps are limited in length. Like you cannot usually produce U, which would be unlimited in length. And the reason is twofold. One reason is because you have limitations, like your motors have finite number of voltage they can accept. Your motors have finite amount of torque they can output, etc., etc. Right? Those kinds of considerations. And second reason is because everything is usually non-linear. So when you think, oh, let's go in one step from here to like, all the way over there, you intuitively understand that it's not going to work. You have to like follow a path or something. So if you have intuition already, and this just sounds to you like a mathematical game rather than a representation of reality, like you cannot in n steps achieve arbitrary output given arbitrary initial conditions, right? Arbitrary like end state from the first state. That's correct, but your intuition is based on physical reality rather than what this problem talks about. So, this dissonance is normal, it is good, but you need to understand what this problem actually says. It does not limit your ability to go as far as you want in a single step, which is non-physical, but it is good for this math. And, the result is important for us. So, okay. But you can still argue, like regardless, what you said is okay, but still give it more steps. The rank of the matrix will increase. Surely, if your rank deficient, surely if your columns are not independent, adding more, if your rows are not independent, adding more columns will somehow randomly make them independent. As in, again, if you have intuition about linear algebra, you know that usually that's how it happens. In a matrix 3 by 3, you may find dependent rows, but 3 by 100, well, very hard to find dependent rows, right? So why not add more columns? The rows will become independent. Very good intuition. Very good intuition. If that's what you have, that's very good. Now, let us study this exact question. To study this question, what we need is a theorem. It is called Cayley-Hamilton theorem, and it goes like this. So this expression, determinant of m minus lambda I, is called characteristic equation of m. You probably remember this characteristic equation because that is how you learn about eigenvalues. Your eigenvalues are set to satisfy a characteristic equation of a matrix, right? I mean, you can just see it. Like this is by definition what we use to find eigenvalues of a matrix, right? Okay, so characteristic equation. So Cayley-Hamilton theorem says that a matrix satisfies its own characteristic equation. So assume that this is a characteristic equation of a matrix. Lambda times n plus a minus 1, lambda n minus 1 plus etc. plus a0. So like we open this determinant expression, it will be nth order polynomial, right? So, big polynomial, solution to the polynomial is the eigenvalue. We can say, put in this equation, instead of lambda, the matrix itself, put m there, right? And the equation will still hold. So instead of lambda, put the matrix m. Instead of lambda everywhere, put the matrix m. Instead of 1 here, put identity. And the equation holds, right? It's very interesting. It's very interesting. It would be, I think, relatively easy to show for matrices for which you can have a eigendecomposition like for positive definite matrices, for example, or matrices where you have this like diagonal matrix of eigenvalues and um, you know eigenvectors on both sides, as I showed in the lectures on stability. I think it will be relatively easy to show that this is correct. I think so. All right, good. But this is a Kelly-Hamilton theorem. So matrix satisfies its own characteristic equation. Very good. Very nice. There is a consequence of this interesting theorem. The consequence is that this matrix m to the power n is, by the way it is written, is clearly equal to a linear combination of the lower power of itself. So m to the power n, matrix to the power n, can be written as a linear combination, those are coefficients, those are matrices, right? Of m to the power minus 1, n to the power n minus 2, n to the power n minus 3, and so on and so forth, all the way until identity. So m to the power 0. So you can see that this highest power, nth power, is a linear combination of lower powers. That is the interesting fact that we're going to use. You remember the linear combination in terms of rank, when we discuss rank, appears in this very interesting place where we say if a column of a matrix is a linear combination of other columns, then matrix doesn't have a full column rank, right? If a row is a linear combination of other rows, the matrix does not have a full row rank. We could also put this a little bit differently. We can say if you add to the matrix a column which is a linear combination of other columns, you do not change its rank. The rank of the matrix is not going to increase, all right? So adding to the matrix a column which is a linear combination of other column does not increase its rank. So that is kind of like where we're going with it. Okay, all right, good. Now let us consider this expanded version of controllability matrix where we add one more term. You know, like here was a traditional controllability matrix: B, A, B, A times A times B, and so on and so forth. I added the one more term. I added the term A to the power n times B. Good. Now, since we have our Cayley-Hamilton theorem, we could say that AN, this matrix right here, this matrix right here, is a linear combination of its lower powers. So it is a combination of a to the power n minus 1, a to the power n minus 2, etc., all the way to identity. Okay. Good. Now, if we multiply this by b, what we get is the same expression, just times b, and so on. Okay. But now notice what we have here. What we have here are elements of this matrix, basically columns of this matrix. Those are columns of the controllability matrix. So what we found out is that from Cayley-Hamilton, it follows that those new columns that we added did not increase the rank of the matrix. So C, the rank of C is the same, C plus is the same as the rank of C, because new columns were a linear combination of old columns. Since the rank did not change, if it happened to be, let's say, n minus 1, let's say the rank was k less than n. So some kind of value of k less than n. Well, follows from this that what do I say? That new columns did not increase k. It's still k, even after we added this matrix. So adding more stuff did not change anything. That's the thing. That is the thing. So somehow, one way or another, we cannot solve the problems that we have by simply considering more steps. And the reason is algebraic. Basically, you can think of it this way. In this n-dimensional space, in n steps, you will be able to do everything that you can do in infinitely many steps. Like it doesn't matter how many steps you take. In n steps, you can do the same because you don't care about how long those steps are. Right? In the real world, the length of each step would definitely prevent you from doing everything in n steps. But here we're not asking about how to actually control a robot. We're asking about whether or not the matrices are degenerate in some sense. If they're degenerate, so not controllable, it means we wouldn't be able to design a controller. Controller, of course, would not do anything in n steps. It would work normally the way controller should. But this fundamental issue of being able to get somewhere would stay exactly the same. If the system is not controllable, controller will not be able to do anything. If it is not controllable, or if it is controllable, we don't have to do it in n steps. We will do it slowly, but correctly. All right. So that is the idea. That is the idea, and it is expressed very beautifully, I think, in a discrete case. Before we move on, do we have questions about what we just studied? Because next we go to continuous case. It's going to be more complicated, and now is a good time to check if you understood.
What's the size of the matrix C?
Size of the matrix E.
Kelly-Hamilton matrix.
Kelly-Hamilton matrix. Sorry, can you on this slide or on the previous slide?
Yep, on this. This each consists of B, A, B, and so on. I don't know how it's called.
This is a controllability matrix.
Yeah, controllability.
Yeah. What is the size?
Yep.
So let me first go 2 slides back. So the size of this matrix first, let me answer this. You didn't ask it, but let me first answer about this. Is basically, we can compute it, right? B has k columns. So B is equal to, let's say, B1, B2, blah, blah, B, K, right? BK. K columns. Can be 1 column, can be k columns. Now, how many does A times B have? How many columns does A times B have? Count them. A has n by n. A is an n by n matrix. So how many columns does A times B have?
Number of rows of A times number of columns of B.
That sounds a little bit optimistic. I don't know. No, I mean,
Shouldn't our matrix B have k rows and not columns?
so B have k columns, right? So B have k columns.
Not
B,
rows?
no, columns. I'm very sure. Of course, like I can be mistaken on any point. Just as any of you guys, right? But I'm as sure as I can be that it is columns, not rows.
Okay.
So B sits in n by k space. So it is a matrix with n rows, k columns. A sits in n by n space. So it is n rows and columns. And it is because obviously it maps x to x, right? So n dimensional to n dimensional. B maps control input, so k dimensional to x, next x, so n dimensional. So A times B, what is the number of columns of A times B?
K columns.
Yes, correct. K columns. Why?
Because we have k columns in B and we multiply it by B.
Yeah. So matrix multiplication goes like this. You take column of the second matrix, multiply by the first. That is the column of a new matrix. Get next column of the second matrix, multiplied by first. Get next column of the result matrix, right? So a result matrix always have exactly the same number of columns as the second matrix multiplication. So this guy here would have to have the same number of columns as B, so K. Now, how many of those multiplications are there in this matrix? Like 1, 2, 3. How many? Can you count?
You mean N?
N, right? So those multiplications are N multiplications, right? Like 1, 2, 3, etc. until like if we count by the power of in front of N, in front of A, we have A to the power 0, to the power 1, to the power 2, to the power N minus 1. So N different units and different blocks in this block matrix. Right? Correct?
Yeah.
Yes. So K times N is a number of columns in C. By C, I mean this calligraphic C, controllability matrix. Now quite clear, right? Whoever asked the original question, sorry, I didn't note your name. Now it's quite clear, right?
Yeah, it's just looks like too many columns, but
Yeah,
okay.
no, yeah, but of course, let's say you have A 10 by 10 and B 5 by 10. Then you have 50 columns. And this matrix here would have n plus 1 times k because we added another block. Any more questions? No more questions, you sure? All right, good. Then let us proceed to continuous time, I believe. Right? No. Before continuous time, let's do the, my apologies, let's do observability in discrete time. So observability. Here, the way I derive it, I use a little bit of a trick. I think it is very good for simplification, but I'm not quite sure if this is the most standard way to derive it. So anyway, let's look at how it is derived. So consider discrete system. Next x equal to previous x times a, previous u times b. Y, the output of the system, is equal to c times previous x. For this system, we know how to get an observer. I'm not sure if we even wrote it down, but as you noticed, the equations of stability are represent exactly the same equations between discrete and continuous systems. So you are not going to be surprised that observer in discrete time is Lumberg observer is next x times a current x, b current u, observer gain L, observer gain L, and output minus estimated output, right? So just one more time, I will run it. Next estimation of x equals to a times current estimation of x plus bu plus observer gain times the difference between actual output and estimated output. So c times x estimated is estimated output. Good. Now Limburg observer written in discrete form. Okay. We remember this trick where we introduce observation error. So difference between estimated state and actual state. We can find a difference between this equation and this equation. U will cancel, right? Bu will cancel. A would be multiplied by error, this estimated error. Right-hand side, left-hand side, sorry, would be just next values error. And there will be this expression, which will be turned into L times C times E, where C is our output matrix. So L times C times E, because Y can be represented as C times X. So X minus X hat is by definition E. Okay, so our beautiful equation, 8 together with equation 7 gave us equation 9. And that is observation error dynamics. That's what we used when we derived observer. This equation is, you remember we said it before, would be stable if and only if this equation is stable, right? There's this dual relation between those two. Like if this is unstable, this is also unstable. Or if this is unstable, this is unstable, etc. So somehow we can try, instead of trying to decide if this can achieve arbitrary state, we can decide if this can achieve arbitrary state. I understand that there is a little bit of a difference between talking about stability and talking about achieving arbitrary state. But if you allow me to sort of like jump over this difference, then maybe by the you can imagine I can make argument something like going from any initial condition to zero final condition, so like final state which happens to be at the origin is the same as stability, right? I can try to make this argument. It's not completely straightforward, but I think it is not completely baffling that I would claim that the fact that those systems are stable together also implies that they're controllable together, right? So hopefully this is not completely like this step feels okay, right? Next, when we have this system, now we can just discuss controllability for this system. It can be written in the following form. Next epsilon is equal to current epsilon times A transpose plus, okay, let me be careful with color coding, plus C transpose times, and here I would note it separately, VI, where VI is equal to minus L transpose E. Okay. So I made this series of substitutions, Okay. In L times E, I describe it as VI. Basically, you can imagine that what I did here is somehow I pretended as if this L transpose E, that is not a that is a linear controller, right? I pretended that this is a linear controller. This is a control gain. It happens to be observer gain, you remember, but I treat it as control gain, and then this becomes my artificial kind of like control output output of the controller. So control input to the plant, control output from the controller. This is the same trick that we used when we designed the gains for observer using pole placement or LQR. We transposed the original system. We said the original system would be stable if and only if the transpose is stable. Then we designed the gains for the transposed system. This is exactly the same, but now we are doing it for observability. All right, if this is our system, let's find out if it is controllable or not. We know how to do it, right? We take this matrix, put it here. Next, we take the same matrix, put it here, but multiply it by this matrix, right? Next, we do it the same thing, but multiply it by the A matrix squared, then A matrix cubed, then A matrix fourth power, all the way until we get A matrix to the power n minus 1. And as before, it's multiplying C transpose, right? So I just use the definition of controllability. It is like, remember, B, AB, AAB, A cubed B, A fourth power B, and so on, right? That is the controllability matrix. So equation 12 is the definition. But equation 12, you can see a lot of transposes. So we define this matrix as a transpose of observability matrix. If we transpose this whole thing, what we get is this matrix O, calligraphic, right? And we have C, A, C, A, C, A squared, C, A cubed, C, A to the fourth power, all the way to C, A, n to the power n minus 1. And this is called observability matrix. Observability matrix. And here's the theorem. The theorem says that for a system like this, with output like this, the system is observable if such a matrix is full column rank. Full column rank. Why full column rank? Remember, we transposed it. So what used to be rows became columns, right? It used to be basically a very tall very wide matrix. We transposed it, so it became very tall matrix. What we care about is independence of the columns. So it has to have full column rank. In other way, rank O should be n. By the way, if you are confused by this like full column rank, full row rank, just think of rank O to be equal to n, rank C to be equal to n. Full column rank just implies that there are no independent dependent columns. Full row rank just implies that there are no dependent rows. But number of rows and columns is n, so the rank of the whole system has to be n, right? Okay, hopefully this is clear. If this is unclear, please ask a question. I'll happily explain. No, it's clear. All right, good. Okay, so this is the definition. This is the definition of observability. Definition of observability. Okay. All right. Now, what it implies, remember, is that we can observe the system. We can find such an observer gain that would get us information about the system, right? Get us information about the system. Okay, all right. So we have two definitions. First definition here for controllability, right? This very nice matrix, very good. Second definition here for observability, again, very nice, very good. But both of them are for discrete case. Both of them depend on this whole argument that in n steps and discrete steps, you can achieve your goal. Right. This argument here rests on the fact that you're making discrete steps in the discrete systems. So for continuous systems, this should be suspect. Right? Looking at this, you should be able to say, well, I'm not making any steps in continuous systems. Continuous systems are about evolution of the state as a differential equation. So why does controllability matrix apply there? Right? Why does it apply there? Okay, it's a good question. It's a good question. Let us try to make an argument about it. So for the argument about controllability of continuous systems, we have to use one more time the matrix exponential. Our matrix exponential is going to be defined like this. You remember we already discussed it. But now we're doing one more piece of mathematics. Using our Cayley-Hamilton, we can prove that any power of A that is higher than n, so any power of A that is beyond n, can be represented as a linear combination of lower powers. So this definition here doesn't actually need to have more than n components, right? All the components after n, like n and higher, are they don't add anything in terms of independent, in terms of how should I put it? They don't add anything that cannot be put in front of these matrices as coefficients. All the higher components, we can consume them as coefficients in front of the lower components. All right. Of course, they contribute to the actual value of the matrix exponential. But we don't have to write them out. Instead, what we can do is we can just find out some sort of coefficients in front of the first n elements in the series. In front of I, in front of A, in front of A squared, in front of A to the power n minus 1. So we can get all of those higher powers to be represented as functions of lower powers. Okay. Good. Good. So that is another result of Cayley-Hamilton. By the way, in case you think that there is a catch, that this is too good to be true, of course there's a catch. The catch is that computing those values is non-trivial. Like how exactly do you compute them? That is completely untrivial. But we don't have to compute them for the proof. All that it is important to us is that there is a finite number of matrices here. That is all. We don't have to compute those combination coefficients. All right. So like this is more practical if you want to actually compute the matrix because it is a complete recipe. This is less practical because you don't know how to compute those functions of time. All right, good. Now you remember another piece of mathematics, forced state response, right? Expressed like this. Forced state response. It is a solution to the system x dot equals to ax plus bu, right? And the solution is e to the matrix exponential times initial conditions plus integral. Here we have this kernel function. I don't know, is it correct to call it kernel? We have a t minus tau times b times u of tau. All right. Good. we have this familiar solution. What we're going to do next, this, by the way, if you think, where did we see it? It was in the lecture on discrete systems. We used this to discretize continuous time systems. So now, instead of this, we're going to write this, right? So phi sub 0, t minus tau I, phi sub 1, t minus tau A, plus blah, blah, n terms, phi sub n minus 1, t minus tau, A to the power n minus 1, right? All of this multiplied by BU. Good. Next. Next, we continue. Have this guy plus this whole expression as before, right? Now we break this expression into separate integrals. Integral of a sum is the sum of integral, right? So we have integral for phi sub 0 times bu tau. Integral for phi sub 1 a bu tau. Integral of phi sub n minus 1 times 8 n minus 1 bu tau, right? So I just broke all of those expressions into separate integrals. What I do next is I notice that we can take this out of the brackets, right? Why can we do this? Oh, because those are scalars. This is a scalar. This is a scalar. So scalars can go in front of a matrix or behind the matrix. It doesn't matter. So we keep those scalar integrals here, and we put, b, ab, a times a times a times b in front of the integration. So we get this expression multiplying, let me be more careful. This expression, right? I want to use this. Multiplying this guy to recreate this guy here. This expression, multiplying this guy to recreate this guy here, right? And so on and so forth. So that is what we're doing here. We just putting this whole expression on the top of the slide into this vector matrix multiplication form. So we have this difference on the left is equal to this matrix times this vector. But now notice this can take presumably any values, right? Presumably it can take any values. I'm not proving this, but maybe you can allow me the fact that on time interval from 0 to t, this can take like any value because of there's like n different functions, and u of tau we can choose to be anything. So yeah, maybe you allow me that it can take any value, right? Of course, if you want to prove it more rigorously, you have to prove that it can take any value, right? But now this vector that can take, again, I'm claiming any value, is multiplied by this matrix, and as the output, it should provide any value here. Why? Well, for the exact same reason. X final, we want it to be something particular. X0, we want it to, it can be 0, for example. So any matrix times 0 is 0. So this whole expression goes away, right? So we want to have any possible output. For that, we have to make sure that this matrix has full row rank, which is our original definition. Of course, there is a caveat to what I showed. Caveat, for example, I used a B as a single column rather than a matrix. we could do it with matrices. I just wanted it to be a little bit cleaner, because if we do it with matrices, this will be a vector. So those would be like vector integrals. Still absolutely correct. Roughly speaking, it will be the same. I just felt like maybe it is already complicated enough. But yeah, it would be roughly speaking the same thing. Okay, all right, good. So you can see that the derivation was less obvious. Like if you consider this guy, let me go back all the way. If you consider this guy, the way we derived it was just sort of, I don't know, a basic exercise in addition and multiplication, you know, very simple. Sure, we had to use this theorem here to prove that we cannot do this, right? This was important. But as long as you convince yourself once about this being useless, the derivation does not need this Cayley Hamilton. Like you can get to the final form without Cayley Hamilton. And it's just that you have assumptions that you have to prove separately, right? So this is very clear. I think that is helpful when you, like, clarity is helpful when you think about those concepts. With observer, right, this is the way I defined it, but derived, you can look for other derivations. They shouldn't be much more complicated, right? But here I feel like this is not completely obvious, at the very least, because inside the derivation you have this whole thing which cannot be computed, so it's hard to understand it a little bit. And here there's this beast, which again we don't work with directly usually, right? But so my message here is that if you're going to work with controllability and you want to think about controllability, what it actually means, start thinking from discrete case. But keep in mind that continuous case is exactly the same. Like the mathematics we use exactly the same. The way we discuss it is exactly the same. It's like more or less identical. It's just the derivation is it, like includes like steps that are not present in discrete case. Right. Any questions about this so far? Okay, I guess no questions, right? Then let me go to the last piece of this lecture. So those are definitions which we use, which are useful and so on, but then slightly impractical. And we need a practical criterion. Why are they impractical? Well, let me show it to you in writing, right? So let's say you have a system with n states. So let's say a robot arm. Let's say it is 7DOF, right? 7DOF robot arm. How many states will it have? Can someone tell me? How many states?
Same of number of freedom, degree of freedom,
States will be equal to number of degree of freedom. You sure?
maybe.
Degrees of freedom describe how many independent motions the robot can have, right?
Yeah.
So it's like number of dimensions in the space of configurations. But also have a space of velocities, right? Each joint can have a velocity which can be anything regardless of current configuration. The answer is 14, right? It's always like this for mechanical systems. You count number of orientations and a certain number of positional variables, orientations, positions, etc., and multiply by 2 because you have also velocities. Actually, counting velocities would be more correct, less easy to make a mistake. So anyway, it's 14, right? Just as the example here, I would say humanoid robot. It may have number of degrees of freedom. DLF would be what would be typical DLF for humanoid robot? Let's say you have 5 degrees of freedom in 6 degrees of freedom in each leg. So it's like 6 plus 6 plus modern humanoid robots have a degree of freedom in their torso. Let's say minimal plus 1. If you have arms as well, arms would have at least 6 degrees of freedom, right? 6. I think, let's assume 6. 6. So total would be torso probably we have not 1 but 2 degrees of freedom at least. So we would have 12 plus 12, 24, plus 2, 26. Let's just say 26 degrees of freedom for the sake of argument. Right? So the number of states would be 52. Okay. Now, controllability matrix requires you to compute the following vector: a to the power n minus 1 times b. Okay. It is unclear so far how it is going to affect us. Let me try to show to you how it's going to affect us. So let's say A is equal to, like it has eigendecomposition, so it is equal to inverse of V times D times V, right? Let's say it is equal to this kind of stuff. Then A times A is equal to basically this, which is when you cancel this guy here, it becomes extended a little bit. It becomes this. And now you can probably believe me that n to the power n is equal to this, right? Inverse of v times d to the power n v. Okay. Now, if the smallest eigenvalue of your matrix, let's say minimal eigenvalue of your matrix is, let's say, something like this. And the biggest eigenvalue of a matrix, let's say it is something like, not 10, right? 10, good enough. After multiplying, you can imagine in computing this guy, this guy here, you have to multiply it to the power 13, n minus 1, right? N minus 1. Why eigenvalue is going to be multiplied from this formula? So in this multiplication, you have 0.05 to the power 13. Can someone quickly calculate for me what this is equal to? Also, what 10 to the power 13 we don't need to calculate it is just 100. Wait, what's the count? It is 10 trillions, right? So 10 to the 10 with 13 zeros. What is 0.05 to the power 13?
I'll write to the chat.
Yeah. Let me see it. 1.2. One second, let me. One point two times 10 to the power minus 17. Okay, very good. Very good. you can see that there is a chance that your computer will decide that this guy right here, this guy, is actually 0. Your computer may decide that it made enough errors to produce a 0, which is represented as 1.2 to the power of 10 minus 17. And the reason is your computer is probably not going to perform those. I mean, it depends. If your computer is smart, like your algorithm is smart, it may actually calculate your matrix A to the power n exactly this way. It is possible. Of course, not all matrices have this very nice eigenstructure. So not all matrices can be dealt with this way, right? So you, and actually I doubt personally, I doubt that you would use this exact decomposition for this purpose. So, it might work very well for only very specific matrices. Yeah. That said, your computer will likely, it's possible at least, multiply those matrices by hand. So you would actually, also you may have written the code this way, like who knows, maybe you've written the code just multiplying matrix times matrix times matrix. It is unclear if your computer would even have like built-in function for matrix powers. It should, like, but maybe you didn't check. So in any case, if you actually multiply matrix times matrix times matrix times matrix, let's say 14 times, what will happen is you will accumulate a lot of errors. Each time it is, each element of your matrix is produced by multiplying n pairs of numbers and adding them together. All of those would have finite precision errors. So they would create errors. Those errors would be very small, like 10 to the power minus 30, for example, like very small errors. But they will continue to accumulate. And next iteration, those errors will be added. Each error produced in the previous step would be added together to create a new element. And effectively, you'll multiply those errors times n each time you perform addition. And you're going to perform those additions, multiplications, etc., n times, right? So it is like n squared, basically, times your error, each error you produced initially, right? I'm not saying that this is a lot. Matrix multiplication is very good in modern software. But for your software, it is unclear whether or not it produced enough error to actually create this guy. Like this guy, for your mathematical software, might look like an error it produced, and for good reason, right? So when you compute a rank, your software may have a criterion, which if you just type rank in, let's say, Python, you would not even know that it is there. But there is a cutoff criterion, which basically asks, is a eigenvalue bigger than a certain value, a certain threshold? It actually is not going to compute eigenvalues. It's going to compute singular values. But you can trust me, those are proportion. They stand in like square root relations with eigenvalues. So they're related, right? It will ask, is this single value below threshold or above the threshold? And it is possible that the answer will be, oh, this singular value actually is below a threshold. So it actually doesn't count. And the rank would drop. Now, you can tell me, all of this sounds very nice, but I'm sure mathematical software can handle n to the power of 14. Like what is like minus 17? Is it really something that precision cannot handle? Well, I'll tell you, yeah, surely. Surely you would be able to deal with it somehow. But this N52, that is unreasonable. Like to me, it sounds already unreasonable. Like I don't even want to know what kind of power I would have here. I'm sure it will be very small power. Like it would be, the number would be close to numerical errors. And values here would be astronomical. 10 to the power of 50, that is numbers that you don't find in engineering. It is just absurd number. So your criteria is very likely to fail simply because your multiplications are too many. Right? And notice we considered here quite extreme example, like one of the eigenvalues was very small, one very big. But for real robots, there often are some like motors which are very like moving something very small. Imagine if you have a hand, like robot hand, one finger joint moves something tiny, right? As opposed to some bigger motors that move something gigantic. It is not difficult to create those situations, right? And as I said, it doesn't really have to be one of the numbers is big, one of the numbers is small. Just enough for one of the numbers to be small. Overall, if you're actually going to use the formulas that we discussed, if you're actually going to use this criteria or this criteria on a big enough robot, you will run into trouble. If you read documentation for MATLAB or SciPy or like any control library anywhere, if you ask to compute controllability matrix, the software will tell you in the documentation that this is not a preferred way to check controllability. It'll tell you not to check controllability using controllability matrix. The matrix is useful for a lot of purposes, like theoretic, but also practical. But software will tell you not to do it for the reasons I just described. Instead, software will offer you something else. Now, let me offer you something else. All right, I would offer you a criterion that you should actually use in practice. So the criterion is, we call it PBH, Popov, Bellman, Hamilton, I think. Hopefully, I don't misinterpret. If you call it Popov criterion, it will be good enough. All right, so the criteria goes like this. You have a pair of matrices, A and B. You want to check their controllability. How do you do it? Well, to do it, what you do is you check if this matrix A minus lambda I, B, right? So it is a block matrix, has two blocks, one block, another block. Right? If this matrix is full row rank, so rank n, has a rank n, then the pair is controllable. But it has to be full row rank for any lambda, not just for some lambda, for all lambda. And a lambda have to be complex. So somehow sounds impossible to check numerically, right? But there is a catch. There is a catch. Let me quickly explain what the catch is. If lambda is not an eigenvalue of matrix A, then by definition of eigenvalues, this is not true. Like a determinant of A minus lambda I is not zero. But if determinant of lambda A minus lambda I is not zero, that means that this matrix already has full row rank. This matrix here would have full rank by itself. Adding B to it does not change anything. It doesn't matter. B, in fact, would be a linear combination of columns of A minus lambda I. So criterion is met. If lambda is not eigenvalue, criteria is already met. So you don't need to check all complex numbers because all except eigenvalues, everything else already checks out. All you need to check is eigenvalues. And since there is only a finite number of eigenvalues of A, you can easily compute them. Just substitute them into this test and check numerically. That is all. You don't have to like go through some kind of like search or whatever. None of this is does not make any sense. You compute exactly the eigenvalues of A, substitute here, check. All right. Yeah. this criteria can even be used for a variety of other things. Like you can check how close you are to be degenerate. Like, for example, if the rank of this matrix is, how should I put it? If the matrix is almost dropping the rank, like if you do a 3D decomposition, you will be able to see the smallest single value. You will be able to say, oh, this matrix is not like it is controllable for rank, for row rank, but it is about to drop the rank. So you can say that it is like controllable, but not like not perfect. There is, so you can even do analysis with this, not just use it directly. All right, but that is it for the lecture because I think we're out of time. But okay, final message. If you're actually doing any practical work, use criteria that are numerically stable. This is an example of a criterion that is numerically stable. You can try to use it. If you are unsure about the criteria, look up how it is derived. Also, double check with traditional criteria. Take into account the fact that traditional criterion is numerically unstable. So you have to be aware of what exactly you are producing in terms of numerical results. But yeah, we have quite easy criterions, and they can even be used in practice directly. Okay, that is it from me. I'll stop the recording and we can answer questions if you have any.